Now, there are two ways to look at the material that's sitting in that separatory funnel. We will talk about the organic layer and the aqueous layer. But the layers are going to be stratified in that separatory funnel, so there's going to be a top layer and a bottom layer. Is the top layer the organic layer, or is the top layer the aqueous layer? Well, that depends. It depends on the solvent that you chose. The bottom layer, the heavy layer, will be the more dense solvent. The density of water is about 1, and so you need to look up the density of your solvent. Most organic solvents have a density less than 1, and so most of the time the organic layer will be the top layer. Density of hexane is 0.66, density of ether is 0.74. They'll all be the top layer. On the other hand, most halogenated solvents are heavier. They have a density greater than 1. So something like dichloromethane with a density of 1.32 is going to be the bottom layer. So it's always going to be important for you to look up those densities and decide which layer is the one you want. Where is your compound? Is it in the organic layer? If so, which layer is that? So keep in mind as you look at extractions that the important thing is not the density of your product. It's the density of the solvent. Your layer is mostly solvent, and so that's the density you want to look up. If you have some doubt in your mind as to which layer is which, just add more water to the separatory funnel. The aqueous layer is the one that's going to get bigger. Usually then you'll isolate the organic layer by opening the stopcock, putting the organic layer into a Erlenmeyer flask with a little bit of magnesium sulfate, gravity filtering, and then evaporating. Aqueous layers, if your product happens to be in there, are a little tougher to get completely removing of the water. Typically, many biochemists who deal with aqueous solutions a lot will use freeze drying or lyophilization in order to get the material out of an aqueous layer. It's important also to understand that the partition coefficient can very much change depending on the pH of the aqueous layer. Most organic compounds are going to be organic regardless of pH, and they're going to be in the organic layer. But there are some organic compounds that we call acids. They're going to be organic soluble unless the aqueous solution is basic. Then the organic acid is now going to be its conjugate base, which will be charged, and it will now go into the aqueous layer. Likewise, there are organic bases. Typically we call those alkaloids. Those are going to be organic soluble unless the aqueous solution is acidic. Then they're going to be in the aqueous layer because they will be charged after they go to the conjugate acid. Here's some examples. If you look at the first compound, cyclohexane, cyclohexane is a typical organic compound. It's neither an acid nor a base, and so it's always going to be in the organic layer. The next compound is benzoic acid. We call it benzoic acid because it's an acid. In neutral water, it's going to be organic. It's going to be this species, and so it's going to be in the organic layer. If the aqueous layer is acidic, it's also going to be in the organic layer. But if the aqueous layer is basic, you're not going to have benzoic acid anymore. You're going to have its conjugate base, the benzoate anion. Now that it's ionic, it's going to be dissolved in the aqueous layer, and so it'll partition to the other layer if the aqueous layer is basic. Here is amphetamine. It's an amine, it's an alkaloid. Neutral, it's going to be dissolved in the organic solvent. If the aqueous layer is basic, it's still going to be a neutral compound in the organic layer. But in acidic media, you're going to protonate that nitrogen and form the ammonium ion. As soon as you do that, it's aqueous soluble, and now in aqueous acid, it'll partition into the aqueous layer. Here's a medicinal chemistry example. In folk medicine, the bark of the cinchona tree was always used in order to treat malaria. This is folk medicine in South America. And so Making a tea from the bark of the cinchona tree was a folk medicine treatment for malaria. In order to find the active ingredient, what one could do is harvest a large amount of bark, boil that in water to form a sort of tea by what we now would call a solid liquid extraction. The active principle is going to be in the solution. For purification, you extract with an organic solvent. That separates all organic components. You extract that organic solution with acid, and as we saw a couple slides ago, all of the alkaloids will go into the aqueous layer. The rest is not alkaloids and is typically not going to be biologically active. If you neutralize the acidic solution and extract the alkaloid back into the organic layer, then you'll get the free base of that alkaloid, which is quinine. Here's a mock-up of what's going on. You take the cinchona bark and you boil it up in water. Throw away the solid, keep the aqueous layer. In the aqueous layer, you then partition between the aqueous layer at neutral pH and the organic solvent. The active ingredient will be in the organic solvent. If you then do a second extraction with an acidic aqueous layer, the active principle is now going to be in the aqueous layer. If you neutralize that aqueous layer and then extract once more, you'll have the organic free base, which is quinine. And this is a typical way that medicinal chemists and ethnobotanists and biologists isolate alkaloids from botanical systems of great interest and isolate the active ingredients. Quinine here is an example. And there is the structure of quinine. You can see the nitrogens. Those are what's responsible for making the material basic and allowing them to be isolated in the typical way of alkaloids. The points to take away then are that if you're given an organic compound and the knowledge that it is an acid, an alkaloid, or neither, you should know which layer it will be in as a function of the pH of the aqueous layer. And so a typical question that might be on a test would be, here's an organic acid, at what pH is it organic soluble? At what pH is it aqueous soluble? Another way of adding to that saying is, if the organic solvent has a density greater than 1, will it be the top or the bottom layer? And so all of those things are going to be easily discerned by you based on the content of this particular presentation. At this stage then, you should be able to understand in a given reaction why you're doing an extraction, where the compound you're interested in is going to be, organic or aqueous, top or bottom, and be able to work through all of that as you process reactions and learn more about chemistry.